Okay, so the fourth video in this cyclic voltammetry analysis series is focused on this fourth tab in the corresponding spreadsheet template called CV Kinetics. And so the focus here is how we can use, once again, scan rate dependent cyclic voltammetry, so the same data set, but to extract a really fundamental important parameter called K, which is also known as the heterogeneous electron transfer rate constant. In other words, it's just like any kinetic rate constant K, but it has to do with how fast electrons are moved from or into the electrode from the redox center of the molecule. We're using the same data set as before. We have a written description of exactly how this spreadsheet works that I've constructed for you. What you need to input to function for this spreadsheet is the same peak potential separation, or delta EP here, as a function of the scan rate here in millivolts per second. So these are the two columns of data that you'll populate. The scan rate column here will then be converted into different units, volts per second, and then inverse square root scan rate, which is important because for this this method of analysis, which we call the Nicholson method, to work, we need to compute this psi parameter, which is a dimensionless, essentially kinetic parameter that comes from the numerical solution to the partial differential equations used to define the shape of the cyclic voltammogram. And so this is the key expression, though you're not going to really use it because I've already sort of pre-programmed it into Excel, but the general idea is that the delta EP, that separation between the two redox peaks, then gets converted into this parameter x, which is a fitting parameter, not really important about its derivation beyond the scope of this course. It's really just the delta E times the number of electrons that were transferred, which is input up here as n. So in this case, for a one electron transfer, they're identical, these columns of data, and then we use that parameter to then compute this value. And this value psi, which is dimensionless. And so once we have the data in the form of psi and the inverse square root of the scan rate, we can make a plot of those two things, which is what we see here. This is the plot of psi as a function of that inverse scan rate parameter. We get this nice straight line. So just like every other expression, we have a linearized form, which is why we're plotting these two parameters against each other. So you can see psi in the sort of red color and the inverse scan rate over here, and k is the value we're trying to get. And so if we look at this in terms of y equals mx, we see that here's y, here's x, and then the slope is this whole composite of terms times this value k. So so the whole slope is this value. So in order to solve for k, we first find the slope of this, which is what we've computed here. So this is already done for you, which is the same slope as found graphically here. And then k is computed by inputting all these parameters in this format. The one key thing that you'll need to remember, and all of this is noted here in the data analysis and calculation for your reference, though you don't actually have to do this. This is just for if you wanted to use this spreadsheet for future use. You can see when we rearrange the slope term here and we solve for k naught, it's just the slope divided by that whole parameter there, and then the inverse square root of that. So that's what this cell in blue is doing, is it's doing this exact computation, and it's grabbing all those constants from up here. I've highlighted in blue the things that you will need to potentially adjust as the experimenter. So one is the number of electrons in the redox event. One is going to be the most common thing, but occasionally you'll have two. And then D is the diffusion coefficient that you computed using the Randall-Sevick equation in the previous video. So if you haven't already done that, watch CV3, the video where I talk about adsorption and diffusion and using Randall-Sevick to compute the diffusion parameter. So this is the same value I computed in the previous video in diffusion coefficient of the molecule in units centimeter squared per second. And so As this changes, you'll need to update this parameter because D is in this final expression. And so it's important that you do this in sequence where you have D. In the event that you have, for whatever reason, a D that's really poorly defined or doesn't seem reasonable, then a good parameter is to just use a value of 1 times 10 to the minus 5, which is exactly what we have. For the compounds that we're dealing with in the solvents we're dealing with, this is a pretty good ballpark number that's going to be order of magnitude for all the first row transition metal ACAC complexes.